Somewhere on a table in a NASA lab right now sits a brick that was never quarried, never poured, never shipped from anywhere on Earth. It was printed out of simulated Martian dust, and it is real, sitting in a real building, which means the single strangest part of this entire story is not the plan itself, tease the fact that half the technology it depends on already exists and has already been tested. This is the story of how Elon Musk's stated requirement for Mars isn't a flag, isn't a photo op, isn't even a city. It's a working factory built entirely out of alien dirt. And by the end of this, you'll understand exactly why the moon isn't the destination in this plan at all. It's the rehearsal. Every step of what you're about to hear has already been demonstrated somewhere on Earth in isolated pieces. 3D printers that build with raw regolith, machines that pull oxygen directly out of Martian air, small nuclear reactors designed to survive 2 weeks of total darkness. And the entire bet is that if you take every one of those separately proven pieces and combine them in the right order, on the right world, in the right sequence, you don't just get a habitat. You get a self-sustaining industrial base that never needs a resupply ship again. The plan begins at the lunar South Pole, chosen for one very specific reason. Certain crater rims there sit in near-permanent sunlight, while the crater floors beside them sit in permanent, unbroken darkness, meaning that within a short walk, you have both constant solar power and ice that has never once been touched by sunlight. Before a single structure goes up, the first task on the ground is simply to look. Ground-penetrating radar scanning beneath the dust to map exactly where the ice sits and how deep it goes, because you cannot build a base around a resource you're only assuming is there. Robotic graders flatten the very first landing pad, adjusting constantly for a gravity just 1/6 of Earth's, where every machine moves, digs, and pushes differently than it would at home. Solar arrays deploy first, because at this specific spot the sun barely sets. But even here there are brief shadow periods, so battery banks are installed purely to bridge those short gaps. A wall of piled lunar dust, a berm goes up early, not for beauty, but for defense. It blocks the blast of exhaust from every future landing, and later it will help block radiation too. A single pressurized rover rolls in next, serving simultaneously as mobile workshop, shelter, and command post, while the footprint of the entire future base is staked out by hand on the ground below it, a grid that every structure from this point forward will be built around. Core drilling confirms what the radar suggested. Real ice, at a real depth, in a real quantity, no longer an estimate from orbit, but a physical sample in someone's hand. A compact fission reactor, small enough to ship, yet powerful enough to run through the full 2-week lunar night, gets installed and wired into buried power cables threading between every system on site, while the communications mast goes up because, without it, every single thing happening on the ground would be invisible to anyone back on Earth. With power, communication, mapping, and mobility all in place, the actual construction finally begins. And it begins, strangely, with dirt. The only raw material available at this location is the gray lunar dust itself, so it gets harvested, sieved into different grades, fine powder set aside for printing, coarser granules kept for shielding and structural aggregate, while magnetic separation pulls out iron-rich particles hiding inside what looks, at first glance, like nothing more than gray powder. Solar concentrators, simple mirrors focusing raw sunlight, heat that dust past 1500 degrees until it turns completely liquid, no furnace fuel required anywhere in the process, and that molten regolith, poured into molds, cools into solid basalt glass blocks, a structural building material manufactured entirely from sunlight and dirt. The same molten process, run through electrolysis, releases oxygen that has been chemically trapped inside lunar rock for billions of years. Oxygen that fills storage tanks destined to become both breathable air and rocket propellant. Finer regolith, mixed with a polymer binder, becomes a thick paste loaded into cartridges that feed directly into a 3D printer. And every single batch of this new construction material gets tested to destruction first against real NASA data, proving it can survive vacuum, radiation, and extreme thermal swings before a single wall is ever printed from it. The printer itself arrives as a massive gantry frame spanning the entire footprint of the first habitat, and the very first printed layer goes down slowly, centimeter by centimeter, forming a circular wall base, while sensors check every single pass for hidden voids or weak bonding as the wall climbs higher. A dome cap is printed separately and lifted into position, the seam sealed by hand, with airlock openings cut only. After the structure is fully solid, because on a printed habitat, the openings always come second, never first. A second module begins printing almost immediately, because no base can survive on a single room. Once the airlock door is bolted into place, it gets pressure tested on the spot, since a single leak here means the entire module fails outright. An interior sealant sprayed across the printed walls solves a problem specific to this material. Raw printed regolith is naturally porous, and without this coating, air simply would not stay inside. Life support ducting threads through channels built into the print itself. Loose bags of raw regolith stack up over each dome's exterior, because a single meter of that dust blocks cosmic radiation almost completely. And as a third module rises, connecting tunnels link every structure together, so crew members can move between rooms without ever suiting up again. Power demand climbs with every new module, so the solar field expands, and a second reactor comes online purely for redundancy, because a single point of power failure cannot be allowed to shut down an entire base. A new foundation, paved in the very glass block this base now manufactures on site, becomes the location for something else entirely, a fuel plant. Water ice extraction begins in a permanently shadowed crater nearby. Heated augers slowly freeing the ice while the resulting vapor is captured and condensed, then split by electrolysis into hydrogen and oxygen, both gases stored separately. Chilled down to liquid form for density and ease of storage. Iron-rich regolith gets smelted into metal ingots, the very first metal ever produced entirely off Earth, rolled into sheet metal and fed into an actual machine shop installed inside one of the domes, complete with lathes and mills shipped from Earth for now, cutting real lunar metal into real parts. A metal 3D printer comes online. Next, producing precision bolts and brackets, and because lunar regolith contains usable silicon, the base even begins manufacturing its own solar panels, at which point this stops being a habitat with some equipment inside it and simply becomes a factory. Power, fuel, metal, spare parts, and solar hardware, all produced from material that was already lying on the ground before anyone arrived. A larger dome rises next, engineered specifically as a greenhouse, hydroponic. Racks and LED grow lights installed inside, and the very first crops go in. Lettuce, potatoes, the same species NASA has already grown successfully aboard the International Space Station, with extra radiation shielding layered over this dome specifically, because plants tolerate far less radiation exposure than the crew does. Tunnels now connect every functional zone of the base, habitat, greenhouse, workshop, and fuel plant, into one single pressurized structure. A paved road links the base to the landing pad to stop rover-kicked dust from damaging sensitive equipment, and a blast wall rises at the pad itself so future landings don't sandblast the surrounding base with high-speed regolith. A full systems test finally checks power, air, water, and fuel together for the very first time as one integrated system. And then it happens. A spacecraft refuels here, using oxygen manufactured entirely on the moon, the first off-world refueling event in human history. After a complete exterior inspection, every seal and panel and shielding bag checked by hand, and a permanent navigation beacon installed to guide every future landing precisely to this exact site, the lunar base stands finished, built from dust, ice, and sunlight, with almost nothing shipped from Earth except the printer that started it all, and then a refueled spacecraft launches, not toward Earth, but toward Mars, because the moon was never the actual destination. It was the proving ground. On Mars, the chosen site is Arcadia Planitia, selected for one specific reason. Subsurface ice sits unusually close to the surface here. The very same survey process begins again, ground radar confirming what orbital data had only suggested, except now there's a real atmosphere to contend with. Thin, but real enough to change how everything gets built, engineered, and secured against actual wind rather than airless vacuum. A landing pad gets graded flat under Mars's stronger gravity, where every machine works harder than it did on the moon, and solar panels deploy at a different angle to compensate for a dustier, dimmer sky. While a larger reactor array goes in specifically because Martian dust storms can block sunlight for weeks at a time, making backup power anything but optional. A protective berm rises again because Mars's atmosphere, while real, still offers nowhere near enough natural radiation shielding on its own. A pressurized rover built specifically for Martian terrain, with different wheels and different suspension entirely, arrives, and when the drill finally strikes solid ice, it confirms the single resource this entire plan depends on. An atmospheric processor begins pulling in Martian air, 95% carbon dioxide, the exact feedstock this base needs, while buried cables link every system together, using the identical method proven on the moon just steps earlier. A communications mast, aligned toward Earth, reminds everyone of the real cost of this distance. A single message now takes between 4 and 24 minutes to arrive, one way. With site preparation complete, using the same disciplined sequence proven on the moon, construction of the Martian fuel plant begins, larger this time, because a return-capable spacecraft here needs far more propellant than anything launched from the lunar base: water. Extraction starts again, heated augers melting subsurface ice, vapor rising and getting captured and condensed, then split by electrolysis into hydrogen and oxygen, while compressed Martian air gets filtered down to pure carbon dioxide feedstock. Here, the process takes its most critical turn. A sealed, pressure-tested reactor combines that Martian carbon dioxide with hydrogen pulled from the ice, using a catalytic process that produces methane and water as its output. Methane being the exact fuel a return spacecraft is designed to burn. The very first methane flows, its purity confirmed on the spot. Gas manufactured entirely from Martian air and Martian ice, now functioning as genuine rocket fuel. Cryogenic tanks, sized for a full spacecraft refueling, begin filling slowly. 900 tons of oxygen, 260 tons of methane, while multiple reactors run in parallel, because a single unit alone would take decades to fill tanks at that scale. Dust brushes installed across the solar field sweep away settling Martian dust automatically, restoring power output after every pass, while the fuel plant runs continuously, water, air, and sunlight flowing in, breathable oxygen and rocket propellant flowing out. The same printer design proven on the moon returns here, reinforced for Martian gravity rather than reinvented from scratch, mixed now with red Martian regolith instead of gray lunar dust, but built on the exact same underlying chemistry. The very first printed layer goes down on Mars using an identical process, just a different color, with even thicker radiation shielding layered on top this time, since Mars's thin atmosphere offers far less natural protection than none at all would suggest. A second and third module rise together now, faster than before. Every lesson learned on the moon applied immediately, without hesitation, connecting tunnels, linking them using the exact design already proven to work. A larger greenhouse dome goes up, sized bigger than its lunar counterpart, specifically because Mars receives less usable sunlight through its consistently dusty sky, hydroponic racks, and LED lighting adapted for a colder Martian interior. A smelter processes Martian iron, even richer here than on the moon, feeding a workshop stocked with lathes, mills, and a metal printer, producing parts from Martian metal. And just like that, a second factory exists on a second world. Fuel, metal, food, and shelter, every bit of it sourced from material the planet already provided before anyone arrived. Roads get paved between every zone because Martian dust turns out to be finer and clingier than lunar dust ever was, and a taller blast wall rises at the landing pad here, since atmospheric landings kick up considerably more debris than landings on an airless moon ever could. Then, for the second time in this story, a spacecraft refuels locally made methane, locally made oxygen, and a return trip to Earth becomes physically possible for the first time without a single drop of propellant carried from home. A final inspection checks every seal, panel, and shielding layer by hand, exactly as it was checked on the moon. And the Martian base stands complete, built using the identical 9-step process proven step by step, first on one world, then repeated faithfully on another. That brick sitting on a lab table at the very start of this story is the same material now holding up every dome described here. A small oxygen-making experiment that once produced breathable air by the gram on Mars has, in this plan, scaled up into the exact chemistry filling an entire spacecraft's tanks. A return flight fueled entirely on Mars, with nothing shipped from Earth for the trip home, is the actual stated requirement behind this plan. Not a flag, not a headline number, but mass, energy, and precisely what you can build from both. None of this exists today, but every single piece of it already does, right now somewhere on Earth, waiting to be combined.